buckle down next couple weeks, but then you'll be smooth sailing.
Is there like a
There is, on the 21st. So the last in-class exam will be on the 21st. We will not hold actually classes that week, so we'll still meet Wednesday of that week for the test, but that'll be it. Yeah.
Will there be another like study session like we have?
Yes. Yep. There'll be another study session.
Is that one gonna count for more points?
What's that?
The midterm is it gonna like
Same as the midterm. I got those at 60 and 60, I think, on the sheet. If after class, if some of you haven't seen the, where you were at midterm-wise, I still got the sheet up here that you can see where you are relative to your classmates and otherwise. Okay, anything else? Yeah. Okay, question is the final exam like the whole thing? And no, it's not. So after the midterm stuff. Yep. So it'll basically be from chapter 10, 11, everything to do with the firm, and then all of those chapters ahead. Yeah. Wednesday the 21st. It's on the syllabus. Yeah, during our normal class time. Yeah. Okay. Anything else?
so that Monday
That's correct. Yeah, we won't have class that Monday before on the 21st. So it's basically this week and next week. And we're done with regular class meetings this week and next week. So buckle down and bear up and bear down and be ready to roll. Okay. So today we start chapter 15, which is our last market structure. So market structures was thinking about the environment that the firm operates in. What is the situation? So perfect competition was one market structure. Monopoly was another market structure, and we talked about the characteristics of each. So those were kind of our bookends. And now we went through monopolistic competition, and today we start oligopoly, which is chapter 15. So oligopoly is our last market structure. Chapter 15, oligopoly. And I'm going to do the same thing we did with all of these and list the 3 characteristics that create this environment for the firm. And so number 1 is that there is a few sellers. A few sellers. Hold on, I want to talk about the sellers first. So there's a few sellers. What do you mean by a few, Russ? Well, a few enough that they are interdependent with each other. So in other words, they're kind of thinking about what the other does because another company's actions has impact on my bottom line. So one of the key features is interdependence of the firms. When we had perfect competition, everybody's a drop on the water in the bucket, right? Didn't matter if farmer Tom, Dick, and Harry, what they did. My little farming business, I kind of operated all by myself because I was a price taker, right? I was powerless in the market. And similarly, in monopolistic competition, we had enough sellers to where there'd be entry and exit that would get rid of all the economic profit. Here, we've got a few sellers that are going to act strategically with each other. Did I see a hand up?
Oh, I was going to ask, would like a good example be like computers or like game consoles?
Yeah, definitely. Computers, there's a lot of different examples. Game consoles would be another good one. So just a few sellers. And so the key about few, or what do you mean by few? So it's a small enough number. Maybe it's 10, maybe it's 2, maybe it's 3, maybe it's 15. 15 is probably getting a little bit large, but small enough such that each firm is interdependent, is kind of the word we give that, is interdependent. What does that mean? One company's actions, one firm's actions has and impact on others' profits. Interdependency. And because they are interdependent, it brings up strategic behavior. You're kind of like coming up with strategies on trying to outthink the other company. So this introduces strategic behavior. Strategic behavior, which we'll spend quite a bit of time on how we handle that. All right, now the rest of them. So I can just kind of tease us up. I'm going to show some data from the textbook like I did last time with monopolistic competition. But let's finish off the list before we do that. Few sellers. Number 2, we can have a homogeneous or heterogeneous good or differentiated good. So it doesn't matter. Homogeneous good. One example in the real world that we'll talk a little bit about is oil. The world market for oil is mostly controlled by OPEC. Anybody know what OPEC stands for? Nolan?
It's like oil producing.
The O is always the toughest one. It's not oil producing, but it is. It's organization. Good. What is it? You got the rest of it? Was that Rob?
Organizing petroleum exporting countries.
Ooh, nice. That might be worth an extra credit point. I'm not sure what brain cell that came out of, or if you happen to have it right in front of you on your notes or something, but either way, you're going to get an extra credit point. History paper. Oh, good. Yeah, that's a hard one because we always want to use oil since it's oil, but it's Organization for Petroleum Exporting Countries. So these countries act together to set the world price of oil. And so that is one of the most famous oligopoly structures that are out there that we'll talk about too. Okay, so oil is obviously homogeneous. As Daniel brought up, if we talk game consoles, those are differentiated, right? I mean, they kind of work the same. We got motion sensor stuff, and we've got our remote that doesn't have a wire anymore. And we kind of go through the similar, but they're differentiated with the type of games you can play and the products that they have. Okay, number 3, we've got some barriers to entry. Barriers to entry, which might be caused by government through patents and licenses and that sort of thing, like we talked about with. So basically, all the same barriers that we had for Monopoly, that hopefully you guys scored well on for your test and homework. Those same barriers are what we're seeing in Oligopoly too. So we got government. There's possibly natural resources. Probably the big one is that there is large economies of scale due to high startup costs. Large economies of scale, usually due to high startup costs in that particular industry. So economies of scale, what was that thing again? What's going up, what's going down with economies of scale? Nope, not demand and price. Not with economies of scale.
Isn't it because your overall economy or overall like market affects the?
No, we're kind of looking at a particular company actually with economies of scale. So it's a company in an industry. What do they observe?
The average total cost.
Average total cost is downward sloping. Now that's a pretty nice technical definition. So talk to me in real world, some real words rather. That is correct. Long run average cost is downward sloping. Somebody other than Chisholm. Good answer though. Good. As the company expands, what? Just want to push that a little bit further. It expands what? In size of what? Employees or production, right? The quantity, the Q. So as we expand production, we have our average cost going down on average. So our picture of economies of scale looked like this. And so maybe an even long run average total cost curve might look like this. And so somewhere over here, costs are getting pretty cheap, but this is at a really large scale of production maybe. Maybe we're producing 1,000 units, and I'm just making up numbers here of what would be large for this industry. But because there was high startup costs, the more I produced, there was high fixed costs. The more I produce, the cheaper these units become on average. Okay, so economies of scale, big thing that we like to emphasize when we got it up there. So this is, of course, part of the reason why we end up having a few firms. That's why it's kind of a big deal, right? So as companies start to swallow each other up through mergers and acquisitions, maybe, if there was, let's say, 4 companies currently producing 250 units, let's say we had 4 companies that had about a 25% market share. There was 1,000 units out there, but we had 4 companies that were currently making about 250 each. So imagine this is the 4 companies. One easy way to gain something on your competitors is to do a merger. If I merge, how many units would my newly formed 1 company that used to be 2 companies, what would be the amount they're producing now? 500. So all of a sudden now we get 500, and now there's 1 company here, and then there's 2 remaining companies. Notice that we went from 4 companies down to 3 now because of the merger. So what is the next likely result here, since the big company now, the big kahuna here, can offer this product not at $100 but at $80 is their average cost. What's the next logical thing for these 2 companies to do? Merge, right? And they're like, oh, we got to compete somehow, these economies of scale. How can we do it? Well, we can merge. And so maybe then we have 2 companies offering the 500 units, and now they're competing again potentially. And then, of course, there's one more step. We can create a monopoly, maybe, if we were allowed to by the government, which might be frowned upon, unless maybe it's regulated or something, and we come up move in that direction. Okay, so that's economies of scale, kind of speaking to the number 1 here of why we might start to see a few firms operating out there. Nolan?
So would an example be like the cell phone industry, how there was just like a couple?
Mm-hmm. Yeah, cell phones would start to be one.
So when they get to 2 companies,
yeah,
if those 2 companies work together to like get past a technological barrier,
okay,
would that be considered a monopoly?
Um,
after they pass the barriers.
Well, I'm not sure I understand what you mean by once they get past the technological, like they kind of create a new product, maybe?
Like how,
oh, joint, you're talking about a joint venture. Okay. So there is something companies do once in a while where they partner together for a particular activity. And so it sounds like you're mentioning research and development, like maybe they're trying to develop a new cell tower that has a wider range or something. So maybe Sprint and HTC or whatever, different companies get together for this one project. That's called a joint venture. They're not really forming a new company. So that's just like for that activity. And that'll be allowed a little more often than a full-blown merger. Okay, so here is from your book again, some oligopolies in the real world. Get these big as possible here. So you mentioned computers and hard drives. Now, how many companies are actually in there? 116. Now, is that a few? That doesn't sound like a very few to me, right? But the red bar is what starts to make the industry characterizing an oligopoly. So we're doing the same thing we did with monopolistic competition. The red bar represents the 4 largest firms. and the percentage of total revenue for those 4 companies. And then the next 4 largest is the green, and then the blue is the next 12. So of that, we start to see that for all of these industries, the smallest here, they have them ranked according to size. The smallest is 60% with telephones. And then batteries, we've got Energizer and Duracell pretty much battling it out up in the top 4. I suppose Rayovac or something is up there. I'm not sure which the 4 are. But we're almost at 90, 91, over 90%, 4 companies kind of controlling the market. Okay? So you see some of the other ones, breakfast cereals. Breakfast cereal is kind of funny. I think that one often gets past consumers. We tend to think that, well, that must be a pretty competitive market. I mean, you go down the aisle at Walmart, and if you look, there's like different colors and boxes and everything, right? But if you start to look close, it's just the same old companies, right? Each one has a zillion different offerings. So it kind of looks competitive, but it's actually not. General Mills and Kellogg make up a large fraction of the 2 even. Okay, so that gives us a little feel. Let's see, I think this was the only thing I wanted to show on this for now. And the modeling for the strategic behavior turns out to be kind of fun, I think. We are going to get away, for the most part, there's a little bit, but we're going to get away from supply and demand and this type of look. So the economic model that we tend to use the most is called game theory, which I've always kind of hated that name because it reminds me of like playing, let's go play some Monopoly and backgammon or whatever, it's game theory. But in reality, it's pretty powerful. So I have proposed to change the name, but that doesn't seem to bode well in academic circles. So, so how to model, we've got kind of the theory of strategic behavior. That's my more formal, powerful sounding thing, I hope. So we call it game theory. And so game theory is an analysis of moves and counter moves by agents, put that in quotes, by agents, and then we'll put parentheses here. What's an agent? Well, it could be a person, a business. We'll talk a lot about businesses. It could be a government. So it's whoever we happen to be analyzing.
Would you put entity?
An entity would probably work, an entity or an organization, but it also includes individuals. So we want it to be kind of, covering a wide variety of people. So in general, we just call them economic agents. So people who are engaged in some sort of activity. So an analysis of moves and counter moves by agents looking to maximize some objective. So, for example, a business might be looking to maximize profits. Okay, so let's just jump right into an example. Suppose there are 2 firms, Coke and Pepsi. 2 firms, Coke and Pepsi. And each firm is choosing whether to go with a high or low, advertising budget. A high or low advertising budget.
Are they doing premiere in the Super Bowl or not?
Yeah, something like that. And maybe, you know, do we hire Britney Spears or LeBron James? You know, do we go high or low on who we want to market who do we want to market our product this year, right? So we're going to make this little 4-square box. And we'll put Pepsi off to the right. And I'm just going to use the abbreviations, Pepsi and Coke up top. And Pepsi's going to choose high or low. And Coke's going to choose high or low. Now, if Pepsi chooses to go with a LeBron, and Coke also chooses to go with a LeBron-ish other celebrity, they're probably not going to both use LeBron, right? They'll have some sort of exclusive. Then Pepsi will make $20 million, and Coke will make $20 million of profit. Now, if they both go with Britney, or Britney-ish type people, they'll save some money, and Coke and Pepsi will each earn $50 million. Because Britney's been charging a little less than LeBron lately. Now, here's the catch. If Pepsi goes with LeBron, but Coke goes with Britney, then Pepsi's going to gather $100 million of profit, and Coke's going to get nothing, zero. And the flip side is true too. If Coke goes with LeBron, Pepsi goes with Britney, then Pepsi's going to get zero, and Coke's going to get 100.
Now what does both go for LeBron?
That's this cell. Yeah. So here's the parts. Now this is your economic model. No supply, no demand. I mean, this is it. This is the model. One of the ways that we'll look at game theory. And so just a couple things to maybe note here. We got these two things are our agents, right? Coke and Pepsi are our agents, or the companies. Each one of them has choices or strategies of high or low in this context. So high and low are the choices, or you might think of it as a strategy. This whole 4-square box is called the payoff matrix. The payoff matrix in general. We are showing profits in the payoff matrix. So the payoff is a little bit more general word to say what is at stake for the agents. And then the way we do this notation in your book, we'll use like some colors, but since I don't have always perfect colors, I might use a little bit of color here, but we also just do the first entry is the agent to the left. So 50, the first entry is Pepsi's payoff. And the second entry is always the agent up top, Coke's payoff. All right, so one thing that hasn't left us, being econ people is being in the prediction business. Where do you think it's going to happen here? If this was the situation, and by the way, the agents know what this looks like too, right? So both Coke and Pepsi can observe this payoff matrix with all the detail. What do you think is going to happen? LeBron wins. Okay, so what does that mean?
They're going to take the LeBron deal because out of fear with the other companies.
Who's going to take the LeBron deal? Both of them. Okay, so you're saying high. We're going to end up here. Okay, does everybody agree with that?
Without proper collaboration.
What's that?
Without proper collaboration.
Without collaboration. So where would they be with collaboration? The Brittany, right? I mean, if they're out to maximize profits and they can work together, this is clearly a better solution for both of them, right? So good. Think about collaboration. So maybe we'd end up here.
But if you're LeBron's agent,
Couldn't they talk about that but then one of them lie?
Okay, so what if they talked about this and then lying? Like they both say, hey, you know, times are tough. You know, Brittany's over on the strip in Vegas. I think she can be picked up pretty cheap, and I think Mariah's over there too. So what do you say? You go, we'll flip a coin. You go with Mariah, and I'll go with Brittany. And, you know, here we go, 50-50. So Jared's bringing up a potential issue with that, right? We have an agreement. Would we expect that agreement's gonna hold up? Kind of tough. Now let's put a little bit of a real world into this. Are Coke and Pepsi able to have a contract like that where they work together on the cost? No, they can't. So that is violating some laws that you'll learn about at the back of this chapter, the Sherman Antitrust Act, and so there's a few laws on the U.S. books that say, hey, Coke and Pepsi, we don't want you working together on this, especially when you dominate the market the way you do. You can't make joint decisions like this. So this would be illegal. Now, has that stopped companies in the past? Okay, so legal schmiegel, we meet for donuts at the Dunkin' Donut, which I heard is closing down some stores now around the nation. And the Coke CEO and the Pepsi CEO says, wink, wink, let's do, you know, the whole M-A-R-I-A-H, and you do the B-R-I-T. You know, they didn't really say anything. They didn't say the real words. But somehow they walked away after coffee and donuts, and this was the deal. Would you predict that is going to be airtight and hold up?
No.
Why? So no, I agree with you, no. What would be your economic reasoning here for that not to hold up? Sam?
well, firms are trying to maximize profit, so one could describe the other and actually cut them off.
All right, so yeah, one screws the other. So there's incentive from an economic standpoint, looking at the model. Is there incentive for Pepsi to cheat? If we agree on this, yes. How much incentive? $50 million. I used $1 million, but 1,000, whatever it works here, right? So we've got double the profit by trying to screw them over. Now, does Coke have an incentive to cheat?
Yes.
Yes, because 100 second entry is greater than 50. So both of them have incentive to cheat. If indeed both cheat, where do we end up? Right back here, right? So that's the type of reasoning that we're doing with strategic behavior. We want to look at the payoffs that are at stake and start to use our economic reasoning to say, well, what's the marginal cost, marginal benefit? You know, where are incentives going to go according to the payoffs? Well,
So, back to the illegal to collaborate like that.
yeah.
Don't they both, that the new system where they're trying to get kids to drink healthier, and they're both on it. So how would that?
Well, I don't want to complicate it too much. I threw a little real world at you, but because then you're just changing the structure of it. So the answer to your question in general is, yeah, we can do 100 of these type of scenarios with different rules of the game. And so you're kind of teeing me up nicely for the next thing I do want to look at. which is the rules of the game. So number one, is this a cooperative or non-cooperative game? This is what Ashton brought up. Cooperative or non-cooperative game? Yeah, and so it depends whether in the real world, like I brought up, it would be a non-cooperative game by law, let's say, that they're not allowed to work together. Again, maybe in that setting, this kind of tees us up for looking at illegal behavior, which is kind of fun sometimes to look at that.
I love breaking the law.
Breaking the law, you love breaking the law. Uh-oh, okay.
Like
We're being videotaped, so be careful.
if they talked about like both choosing the low, wouldn't you still like in reality you still want to make actions in your own best interest?
Yeah, and so, I mean, so that's what's not, the economist in us wants to say, will they be acting in their best interest if they stay with this? And so the answer is no, if we're narrowly defining this as profit maximization, I don't care about anything else, integrity's out the window, blah, 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 right? So again, we kind of have to look at the rules of the game on what we're doing when we make this prediction. So good. So cooperative or non-cooperative game. So in general, can agents work together? Question mark. This is called collusion. Collusion is kind of the fancy word we use for whether we collude with each other. We can exchange information and work together as one. Collusion. Okay, so does this game change for you if I told you we were going to play it 100 times? Would that change your answer if we knew it was going to be played 100 times? Not just once, but 100 times. Would that change the outcome? You know, how would the game be played? Might it be played differently by either one or both of the agents? Even if let's say it is a non-cooperative game.
Are you asking like for risk assessment?
Yeah, you want to probably do a little bit of risk assessment. What might be a strategy you might think about if we were playing it 100 times? 100 times in a row, by the way, as we play it.
The first couple of times you see it, like if you do meet up and talk, you might see how trustworthy they are.
Yeah. So maybe we didn't even have the coffee, but we both are looking at this thinking, we got 100 times to play. I'll play Brittany for a couple times. Maybe that idiot over at Coke will start to figure it out that, hey, we can both be made better off if he starts using a Britney-ish celebrity. If he goes with Mariah or something, then we might be in the money for the next, who knows, 90 times or something, right? And occasionally, yeah, you might get the 100. When would be the ideal time to play the 100?
The last game.
The last game, yeah. So, that Pepsi is thinking, oh, yeah, okay, I got it. We kind of got the rhythm of it here. I got an idea. I'm going to play high on the last time. And then Coke is thinking, wait a second. I got an idea. That Pepsi's pretty smart. I bet he's thinking that he's going to play on the last time. I'm going to play it on the second to last time. All right, so I'm going to be on the 99th trial. And then Pepsi sits back and thinks, wait a second, Coke's pretty smart too. Probably think what I'm thinking. He's thinking that I'm thinking I'm going to play on this. So now he's going to go on the 99th. I'm going to go on the 98th. And then Pepsi starts thinking, wait a second, he's probably thinking that I'm thinking that I'm going to go on the 97th. I'm going to go on the 96th, 95th, 94th, 93rd, 92, 91, 90. Yeah, that's about enough workout for me so far. Where does that logical thing end? When does it logically end? All the way back to 1, right? It unravels itself logically. If we play that game out under that set of circumstances, the game will unravel itself back to this being the smartest position to play so that you don't get screwed over somewhere in between as you start to work through that strategy.
But if you look at the odds, if they both went, say, like you said, Pepsi says, all right, I'll play Brittany a couple times and maybe Coke will figure it out. If you do that and Coke plays high in the first place because that's their odds, he's going to stay on the high side because he's making 100 over 0.
Right. So
he's never.
if you always play high, if you're the one that figures out that logical string and you always play high, will you be made better? For sure. Yes. If the other person's playing I'll dabble a little bit and see if he or she's playing smart. Well, as soon as they get screwed a couple times, you're up. You're up better than what you were before. So you've already won by allowing the other person to play the little dabbling game. And so it's better to just play high if they're both kind of equally strategic with each other. All right, so what if I change that rule now to we play it indefinitely? In other words, there's no ending. Instead of 100 times, it's like we're playing forever, or we don't know when the end time is. Would that possibly change how you play?
After a few times it hit high, they're going to start discussing and saying, okay, we can both benefit.
Possibly. We want to avoid maybe there being discussions. So without an ending time, I can't play that last, I'm going to screw you on the last time, right? So now all of a sudden there might be a strategy that might make sense for you to play it if there's not a known ending time. So we got all these little nuances that come out of this game theory stuff, which makes it kind of fun. So our second rule of the game that we should know is this a repeated or one-shot game? Is it a repeated or one-shot game is the one time. We call it a one-shot game. And if it's repeated, is it a finite game or an infinite game? So is it finite or infinite? Finite just meaning X number of times. 100 times, 2 times, 3 times, 4 times, a finite game in a repeated game. Or infinite just meaning no ending specified. Okay, one more curveball to throw at you. What about if we played a sequential game where Coke gets to move first and then Pepsi moves? So Coke moves first, Pepsi will see what Coke did and then gets to make a choice. Does that change the outcome of this game if we have what we sometimes call a first mover advantage, right? So Coke gets to go first, then Pepsi follows. Will that change the nature of this game? Yes? So does that change the outcome of the game? I hear a lot of yeses.
They won't get screwed over. They'll be great. They'll both either one or the other.
So how could we go about thinking this through? So if you're Coke and you get to go first, talk to me about maybe the logical thing you might do of which one should I choose? I'm in the power position. I get to choose high or I get to choose low. Man, this 100 looks good and 50s look good. I mean, what's my real decision?
I'm choosing high because I don't want to choose low and then choose high.
Okay, yeah, so despite you being in the power position, we might end up at the same spot. And we do in this case, because if you look, you're in the power position, so you say, okay, what if I chose high? What would Pepsi choose? High, because 20 is greater than 0. So we know what we're going to get is 20, because we know if we choose high, we're going to end up here. If I choose low, what is Pepsi going to choose? High, because 100 is greater than 50. So we know for sure Pepsi's going to go high. Even though I get to call the shots first, that means I'm effectively being Coke, choosing between 20 or a 0. This phantom thought of, oh, I can make lots of money, or I could make 100, or I could come make 50, really evaporate. There's no way you're ever going to do them. So they end up being what we call a dominated strategy. That strategy of low ends up being dominated. It's not ever going to be chosen. It's not ever going to be chosen. So we end up having high. Of course, you go high, they go high, we end up at the same spot. So it actually didn't matter that we had somebody able to go first. So that's called a sequential game, though. It's an important rule of the game. So rule number 3 is the game sequential? Sequential or simultaneous? Sequential or simultaneous? Sequential means take turns. Take turns with your choice. And you get to see others' choice. If you're the second person afterwards, you'll get to see what they chose. Whereas a simultaneous game is either A, at the same time. That's what we usually think with simultaneous. If something happens simultaneously, it happens at the same time. But that's not what we need here. It doesn't have to be the exact same chronological time. What's the important thing we need to have happen if we're playing a simultaneous game? You don't know what the other one's chosen, right? That's all we need. So it doesn't matter if Pepsi chooses on Monday and Coke chooses on Thursday. As long as Coke doesn't have knowledge of Pepsi's choice, we have a simultaneous game, or what we call a simultaneous game. So simultaneous games are choices are made without knowledge of the other's choice. So choice made without knowledge of others' choice. Okay. So the game that we played, just to make sure with the outcome that we got, I was trying to set up a non-cooperative, one-shot, simultaneous game. If I was laying down the rules ahead of time, and I told you, okay, here's the game. It's a non-cooperative, one-shot, simultaneous game. Go, give me an answer. That's how it would work. We're kind of setting up the rules of what the agents know or can do. So
For the sequential one, can't that also hurt even the person who goes for or goes last because they choose, but then they see that the customer has already bought their item and now they can't do anything to it?
it depends on the timing of what happens, but yeah, I mean, in general, if you're choosing last, then you can predict which one, you being the other player, can predict which one that person's actually going to choose in a sequential game. Yeah, so one of the things you do that, I don't even know if the book does it, but hopefully you guys can get this. You're bringing up the concept of backwards induction. So with a sequential game, since you brought it up, it's a good insight. We don't get into games that are too complicated with the principles introduction here, but so note, with sequential, you can use backwards induction. Basically, backwards reasoning. Start at the end and work your way forward, which is kind of what I did with the 100th, the 99th, the 98th, and kind of work backwards. So with a sequential game, that last person that gets to choose, we kind of start there and then work our way backwards through the game. Okay, any other comments or questions? All right, so I've got some tips for how to solve games. So tips for solving games. the first thing that I've always done, and you don't have to, these are truly tips, but I think you'll find it helpful to kind of have a playbook to go to. This is the way I've always gone about it, is to first look for a dominant strategy. A dominant strategy. And this is a choice. Dominant strategy is a choice that makes an agent, better off, a choice that makes an agent better off no matter what the other one does. No matter what the other does. So it kind of looks like what we did sequentially, but to look for a dominant strategy, we just kind of look at the other person and what they're doing. So for Coke, for example, if I want to look at, does Coke have a dominant strategy? So for Coke, from our example, if Pepsi chooses high, so I'm using a little bit of shorthand notation, if Pepsi chooses with the arrow high, if Pepsi goes high, then Coke should go what? High. So in the payoff matrix, when you're looking at the numbers, you might want to kind of blank out the information that's not needed. If Pepsi goes high, we can kind of blank out the low choice, and then we can say which one would Coke want to go with. They're going to go high because, remember, Coke is the second entry. This takes a little bit of eyeball training, by the way. Coke is the second entry. 20 is greater than 0, so Coke would choose high. So if Pepsi goes high, Coke chooses high. If Pepsi chooses low, then Coke chooses high again. So let me go ahead and write that out and then look at it.
So essentially, with the 50-50 outcomes eliminated.
Yeah, kind of, that's right. It's essentially going away, but try not to think of it as the 50-50 outcome being eliminated, but really the strategy of going low has been eliminated, right? For both players, low has been eliminated, which essentially knocked out this, and this, right? But you're right, conceptually that one kind of goes away. So if Pepsi goes low, now we kind of let our eyeballs blank this out. Which one would Coke want to choose? Well, 100 is greater than 50, so Coke would choose high. So if Pepsi goes low, then Coke chooses high. Since you've got the same answer here, Coke has a dominant strategy of high. Therefore, 3 little dots is kind of a math symbol for that. I can't remember if I've used that much in class before. Therefore, Coke has dominant strategy of high, since these match, since we get the same outcome here. Okay, I saw a hand up. No?
Is there any strategic advantage for going low?
Not with this game. Nope. And that's kind of what we're reasoning out, is that in a non-cooperative, one-shot, simultaneous game, you've got one choice to go. Both players are looking at this. This is the best strategy to pick.
So don't you already know the outcome of the game then?
We do, that's right. So we're basically making a prediction of where we think the game's going to go, and I'll come back to that point in a moment. So we can do the same story. Notice that this was for Coke. We were trying to determine whether Coke had a dominant strategy. Does Pepsi does Pepsi have a dominant strategy? Do kind of the same exercise. If Coke goes high, what's Pepsi going to choose? High, because 20 is greater than 0. I didn't give you guys this trick the first time, but one thing you can do, even if you're using the same color pen or pencil, is if you circle the first entry and then circle the player to the left, the circled entries are always that player's outcome. So again, if Coke chooses high, Pepsi chooses high because 20 is greater than 0. If Coke chooses low, Pepsi chooses high because 100 is greater than 50. Therefore, Pepsi has a dominant strategy of choosing high. So in this particular set of circumstances in this game, both players have a dominant strategy of going high. Okay, questions on that? So if you want to put that note here, I'll let you guys do it on your own, but I'm just trying to squeeze in here. Pepsi has dominant 2. And you guys can prove that on your own. You can kind of go through that same exercise if you want. All right. So tip number 2 is to look for a Nash equilibrium. So right away when we hear the word equilibrium, what are we thinking? What's coming to your mind besides pain and anguish when you hear the word equilibrium? Outcomes that are equal? No, there's something that's kind of equalizing, but I wouldn't say that it was some sort of fairness like equal that way. Equilibrium, yeah. Nolan?
2 things kind of cancel each other out.
Okay, they're kind of canceling, yeah. Long time ago, I gave you the definition for equilibrium. If you flip back in your notes to maybe the second week at most, first or second week, I gave you some definitions for equilibrium. First one to find it gets an extra credit point.
Situation in which there is no tendency to change.
Bingo! You found it. Nice work. All right. Let's see. Is it? No, you're not, Dustin. Where's my sheet? This is my old one. Give me your name again. Oh, here it is. Austin. Yeah, I knew it once I saw it. There it is. All right. So Austin's got it. In general, I just like to think of a situation in which there's no tendency for change. A situation in which there's no tendency for change. So tip number 2 is to look for a Nash equilibrium. A Nash equilibrium. So, a Nash equilibrium. So, a guy by the name of John Nash, who was a famous economist slash mathematician that earned the Nobel Prize in economics. What was your question? John Nash. Yep, John Nash. So he kind of went crazy. Anybody see A Beautiful Mind? Show of hands, A Beautiful Mind. Do you remember the title? That was about John Nash's life story. And so if you haven't seen the movie, go see it because it's a great movie. Even for it, you don't have to be an econ junkie to get a kick out of it. So it's a good movie in its own rights. He ended up going kind of psychotic. So there's some interesting stories there. But before he went too crazy, he developed this game theory stuff. This is really his work. So he's kind of one of the pioneers of game theory type work. And so the equilibrium that he thought came up with strategic behavior is that similar to the situation where there's no tendency to change. So taking as given what your opponent has done, would you like to switch? Is there a tendency for change? So taking as given what your opponent has done, would you like to switch? So with this outcome here, I'll write that out in a moment. If we look at the 50-50 and we said taking as given, if I'm Coke, taking as given Pepsi going low, would I like to switch my answer? From I'm currently at low, I'm Coke, would I like to switch my answer? Yes, because 100 is greater than 50. Therefore, Nash said this is not a stable outcome. There's incentives for people to switch, and when the incentives are there, people tend to switch, just like we saw what Jared pointed out with the cheating on the arrangement, right? So that is not a stable outcome, and so it's not a Nash equilibrium. All right, so Nash equilibrium is a choice combination or a choice set, a choice combination such that neither player, neither agent, a choice combination such that neither agent wants to switch / change their choice, taking as given the other's choice. Neither player wants to switch. Underline neither. Once you identify that one player wants to switch, it's not. You can just move on to the next one, right? Because neither player has to be able to want to switch. So let's come up to, let's kind of, I told you this is a tip for solving games. So one thing you can do is just pick an outcome and say, would anybody like to switch? So 50-50, would anybody like to switch? Yes, 100's greater than 50. That's not a Nash equilibrium. Let's come up to here. Would Pepsi like to switch? No, right? Pepsi is the circle. Pepsi doesn't want to switch. 100 is greater than 50. Ooh, we got a possibility. But would Coke want to switch? Yes, because 20 is greater than 0. Therefore, it's not a Nash equilibrium. So it's possible to have one not wanting to switch, but the catch is that neither player wants to switch. And that brings us, of course, to this solution. Does Pepsi want to switch, taking as given what Coke has done? No. 20 is greater than 0. Would Coke like to switch, taking as given that Pepsi's going high? 20 is greater than 0 for Coke. So the answer is no. Bingo. We've got a Nash equilibrium. So how we sometimes notate that is we put a little N in the upper right-hand corner of the cell to say that that's a Nash equilibrium. And that, of course, ends up being a possible outcome for the game. All right, so that's kind of our story here for Coke and Pepsi. Does anybody have any questions at this point? So dominant strategy. Oh, Sam?
Are these fixed costs, like with the advertising rate? Is it a fixed or variable cost? Like, can it change?
In this particular context, we're usually going to be restricting to whatever you see here.
Okay.
So if you know that it's a one-shot game, whether it's fixed or whether it's variable, we might not even know that information, nor do we need it to analyze the game.
Yeah, 'cause I'm just like trying to think like back to long run and short run, would you like end up seeing some sort of balance or it all ends up around the same? Or?
So yeah, and that as far as a long run, short run thing, we don't have that same distinction with game theory in analyzing the game.
Yeah.
A lot of times it could be over a long period of time or it could be over a short. If this is just kind of a snap decision, this is coming up, this very well might be a short run in the context of at least one factor of production's fixed, which is our definition for short run, or it could be a longer term outcome. So we don't have that same distinction. Good question.
In this game theory stuff, would it only be
that chart between two companies, or would there be one for like 4 different companies?
Okay, yeah, good question. We saw a lot of things with the 4 companies. It might be 2. So you're bringing up a couple things. One thing, when we look at 2 firms, we call it a duopoly. So we got oligopoly, which is multiple firms, but one of the words that you'll see in the textbook this week is duopoly. So 2 companies making the decision. There can be multiple firms that you bring in. It kind of it can get a little bit ugly because now we might have a cube, right? We got the Rubik's cube here. If we have another dimension from 2 dimensions out to 4, so if we got high, high, all of them going high, high. If this is a Rubik's cube thing, we'd be out in another cell. So we don't do that in principles class. So, but we can have choices, and what we usually see is the setup of the game might be handled a little bit differently when we have 3 players making decisions. So, but we won't get that complicated. But the answer is you can use this tool to analyze that stuff, yes. Now, if there's more, secondary part, I think, to your question, is what if we have high, low, and very low? Like, we're not talking Brittany or Mariah, we're talking who?
Jared.
Who? Jared, yeah, there you go. Let's have Jared market our stuff. He can be picked up really cheap, right? So we got very low. Now, if we have a very low category, we just have another set of outcomes that we need to add on, right? So this could turn into a 3x3. It's possible that Pepsi only has 2 choices and Coke has 3, and it would look like this, right? They don't have to have equal. Maybe Pepsi's got 4. Don't draw this on your papers, but you know, maybe Pepsi's got 4 choices and Coke's has 3. Then we're just going to look at what the possible outcomes are with all those choices. Okay, yeah.
So if it's a duopoly, like it's in the firm's best interest to outcompete the others, but isn't it also incentive not to get too ahead because then would that create a monopoly?
So all of that would be embodied perhaps in the outcomes. So anything that affects the payoffs is going to be included in these numbers. And so that's going to dictate our choice, that we've hopefully carefully analyzed that this is the payoff if this happens over this time frame. Okay? Anything else? All right, well, let's see. Let's see how well we got this stuff. Let's do a new one here. All right. So we have a young couple that's madly in love with each other. Yeah, that would be kind of nice if we could hit a button and have it all shook up. That'd be kind of cool. So 2 young lovers are trying to figure out where they're going to go this Saturday. They've got a big dilemma on their hands because UFC 186 or whatever the heck they're on, the big fight where the biggest, baddest dudes in UFC history are going to clash this Saturday. And at the same time, the Russian ballet is in town. And the greatest ballet dude of all time is going to be there. And unfortunately, the times are at the same spot. And so this young couple has quite a dilemma. And we're going to analyze that with game theory. So we've got Netflix and all right, so here we go. We got Pat and Chris, and we've got the ballet and the fights. So they're madly in love with each other, and so if they go to the fights that night, Pat gets 3 units of satisfaction, 3 units of utility, whereas Chris gets 2 units of satisfaction. If they go to the ballet together, that's just reversed, where we've got Pat getting 2 and Chris getting 3. Now, if they go their separate ways, Pat to the fights, Chris to the ballet, then each person gets 1 unit of satisfaction. And finally, if Pat goes to the ballet, Chris goes to the fights, they both end up with a big fat 0 units of utility each. Okay, so let's use some economics to help this young couple out. Where are they going? Saturday night. Where are we going? Wherever she wants to go. Well, you got yourself a problem because these are 2 females. So, sorry. It's Pat and Chris, because he said just go where she wants to go. So that raises a problem when we've got 2 females here are at this issue. So, all right, we got Pat and Chris, 2 young lovers. I didn't expect you guys to be so gender biased. Gosh, this is college, for crying out loud. You immediately assume that we have a female and a male here. So, ask the lady. Well, now you're back to the gender biases. This could be Pat and Chris. This is 2 guys, maybe. Same thing, right? So, let's use our strategies. Dominant strategy. Check for a dominant strategy. I'll walk around the room, look at what a dominant strategy is, and tell me whether Pat or Chris have a dominant strategy. That's a good way to start solving the game. Dominant strategy. A choice that leaves somebody better off no matter what the other one chooses. Now, what I'd like to see you write on your papers is the way I tackled it, because you might need to do this on a homework or a final exam. If Pat chooses this, then Chris chooses this. If Pat chooses this, then Chris chooses this. Use that technique to determine whether there's a dominant strategy. Did this thing make it around, everybody? The sign-up thing? No. Still going here? Got a haircut, huh? Looking good, looking good.
Either way, she gets screwed.
Does either player have a dominant strategy?
If it was like you said sequential, if you knew what Chris was going to choose, you would choose the same thing as well.
Okay, so good thing to bring up. You know, what are the rules of the game? Let's say that this is a simultaneous, 1-shot, cooperative game though this time. So not non-cooperative. We got a young couple, of course, they can talk to each other, right? So we got a simultaneous, cooperative, 1-shot. The fights are this Saturday, and that's it. This game's over, baby. This is it. Is there a dominant strategy?
No.
No, there's not, right? So hopefully you guys saw that on your paper as you worked it through. Let me kind of work it through on the board. So checking for a dominant strategy for Chris, if Pat chooses to go to the fights, what should Chris do? Go to the fights, because 2 is greater than 1. So we're back to eyeball training. Again, you might want to circle the payoffs for one or the other. So in this case, notice I switched it on you, just to kind of help identify them, right? So 2 is greater than 1, so you're going to choose the fights. If Pat chooses the ballet, what should Chris choose? The ballet. So now we got one direction going with the fights, one going with the ballet, no dominant strategy. Then we want to check for the other person. if Chris chooses the fights, what should Pat choose? Fights. 3 is greater than 0. Right? So Pat will maximize utility by choosing the fights. If Chris chooses the fights, what should Pat do? Ballet, because 2 is greater than 1. So no dominant strategy. So in this case, neither player has a dominant strategy. All right, tip number 2, Nash equilibrium. Are there any Nash equilibriums here? So Nash equilibriums, yeah, Blake?
Would that be where both of them get 1 unit of satisfaction?
Down here?
Yes.
Okay, so Blake wants to test whether this is a Nash equilibrium, right? So what's our test? If we start here at fight ballet, what's our test for a Nash equilibrium? See if either party wants to switch. Does Pat want to switch? Yes, because 2 is greater than 1. Boom, not a Nash equilibrium. Okay, now the next natural one to do is probably this cell. Because does Pat want to switch? No, it's just what we just said, right? So 2 is greater than 1. Does Chris want to switch? No, because 3 is greater than 0. So we got ourselves a Nash equilibrium.
There's the other corner as well.
All right, and then we got this other corner Jared's saying, right? So you can go around to each one. Little hint for you on Nash equilibrium. So here's your extra tip. If you've found a Nash equilibrium, there's no way that the cell next to it could be a Nash equilibrium, right? For the same reason we just did here. Like this one wasn't, we went up. There's no way now that either one to the side could be a Nash equilibrium. So the only one left to test is what Jared said to test is this one. We come down here, would Pat like to switch? No, because why? I just want to make sure everybody's tracking. 3 is greater than 0, good. Would Chris want to switch? No, 2 is greater than 1. Ooh, Nash equilibrium. All right, so yeah, where are we going to go? We got 2 equilibrium. Now this is already weird from what we did all this whole semester, right? 2 lines cross, equilibrium price, equilibrium quantity. There's only 1 equilibrium. Now we have a possibility of multiple equilibria. So 2 of them here. So where do we go? Young couple. I heard flip a coin. Okay. What else? Whatever's cheaper. Now that's a good one. I'm going to throw that out the window though. Yeah, if this is marginal utility, I can make these marginal utilities per dollar, right? So I didn't give you enough information, but you're absolutely right. If these were just utility numbers, marginal utility without taking dollars, if UFC is twice as much as ballet, then that might be a factor that would actually change the payoffs. We'd have to kind of recalculate. So let's just assume that these are marginal utilities per dollar. Marginal utility of the fights divided by the price of fights is how we equalize that, and marginal utility of the ballet divided by the price of ballet. So we've kind of equalized those things in the payoff matrix. But great comment to make. What else? Yeah.
Is there like opportunity cost more than just dollars, but units of happiness?
Okay, so yeah, possibly if we had some driving expense or something. Is that what you're thinking? Like,
I'm talking like more of the benefit rather than cost.
Well, we've got the benefit and the price all wrapped up into this. Okay. So that's really taken into account. This is how much happiness that Pat gets per dollar spent, okay, right? So we've kind of done the happiness thing, and then we've normalized it by the dollars. Okay, yeah, we might have another variable added. Might be a way in the real world that this gets solved anyway, right? Is Pat getting any fringe benefits? Wait, by the way, which one does Pat like? Which one is Pat? Is Pat the fight liker or the ballet liker? The fight liker, right? So if they get to go to the fights, even if they go solo, Pat still gets 1 unit of satisfaction. Not as much as if his or her lover is along, get a 3 if that happens, right? So we get this extra bonus. Okay. So anything else for where they go?
Do they last the same amount of time?
Do they last the same amount of time? Yeah, so we might analyze time or something. And again, I'm just going to lump that in. That's a great real-world question that could be lumped into the utility. But you're absolutely right. Could be time. Might be some other factors. Bring in some other variables. You know, fringe benefits. If you do this, then I'll do this. You know, some sort of contractual arrangement of if I get my way, then you got to give up something. But we don't have any of that detail here in the model. So the best we can do from the economic model standpoint is just to say our prediction would be they're either going to go here together or they're going to go here. Right? So we've narrowed things down. We haven't come to a single conclusion, but at least we've narrowed things down. We've used our economic reasoning to say they're going to go one way or the other. Okay, questions?
If they both go to the fight though, they both have a 2-point increase in satisfaction over the ballet, which one has 1 point and the other one has 3.
Yeah, it's the same. It's just mirror images of each other the way I got the numbers. So, and we're not going to allow interdependent utilities, but this thing is really called the battle of the sexes. This was a real thing in an economics journal, and it was basically told the way I did, short of the gender thing. They used gender bias. I think it was published in the 60s. And you better believe it that the guy was the fights and the girl was the ballet. They didn't, you know, there wasn't too much PC going on in the 60s at that point. So it was called the Battle of the Sexes with the name of this game and how it played out. And the thing we get from it is that there's a possibility for multiple Nash equilibrium. So we got 2 Nash equilibrium. So we were able to narrow things down. We were able to narrow down the possible choices. All right, and so the flip a coin answer ends up being a good possibility of how we might solve this problem with multiple. So this is also called more generically, that you'll see it in the book. This is a game of chicken. We got all these fun titles in game theory, which is kind of fun. A game of chicken. Does anybody know what the game of chicken is like in real world now? If you're playing a game of chicken with your friends or something, what are you doing with that?
First one to bail.
First one to bail is the chicken, right? That person loses. So if we put that into a game theory framework, right, we can think about the winner and the loser. And so we bail out, we have a loser. But if both continue on and both aren't chicken, do they both win or lose? They both kind of lose, right? So we have 2 Nash equilibrium. Those are one bailing out and the other one staying strong. And then the flip side of that, the other one bails, the other one stays strong. Those are our 2 equilibrium. And so that's our game of chicken. So let me write that out. I mean, the traditional game of chicken was, if you've seen some old movies, you know, 2 guys that were trying to out-macho each other, driving their cars. Yeah, Footloose does it, doesn't it? Yeah, with the tractors. So they're heading head-on with each other, and that's the deal. Whoever veers is the chicken and loses, right? Otherwise, if they're both too macho, they both potentially die. So game of chicken, 2 cars running at each other. the chicken bails out and loses. So then we start to really get into head games potentially with the game of chicken, and we might get into more details about how much do I know about my opponent and other things that might go on. Okay, so got another game. Another game, yep, we're having so much fun here. This is called the game of matching pennies. Matching pennies. All right, so who's got some coins? I don't know if I have any here. I need some game. We're going to do a real life demonstration here. Who's got some coins? And I, of course, don't have any, so let's see. Jennifer's searching. Just a couple quarters. They don't have to be pennies. So a couple quarters, couple nickels, couple dimes. Oh, Dirk's got them here. Okay, so we could use pennies, I suppose. But yeah, let's do, since you got pennies, it's very rare that I have pennies. So Dirk has a penny, I've got a penny. So Dirk, take that. Oh, you're going to get set up here. So each player has a penny. So it's Dirk and I. And each player chooses head or tails without the other's knowledge. Each player chooses head or tail without the other player's knowledge. So go ahead and do that and place it on the top of your wrist. Pick whatever you want. And then on the count of 3, we reveal them. 1, 2, 3. And if they match, then player 1 wins. If they don't match, player 2 wins. Now in this case, they didn't match. He had tails, I had heads, and so I'm player 2, so I win. So that's how the game works. Hopefully you guys got that. Thank you, Dirk, for. All right, so I'm going to write down those rules, but I just told you the game. This time I want you guys to set up the game in the game theory framework on your own. So I'm going to do the rules here. So number 1, each player has I guess let's go player 1 and 2, or you can do Dirk and Russ if you want. Player 1 and player 2 has a coin, has a penny, since we were able to use a penny. Each player has a penny. And number 2, each chooses heads, or head or tail, without the other's knowledge. Number 3, at the count of 3, each coin is revealed. And step number 4, if they match, player 1 wins. If they don't match, player 2 wins. Okay. So I want you guys on your own to develop the game theory setup for this. Develop the model. And then I'm going to come around and randomly select some of you to come to the board and show your work on how you did it. All right. So, Drex, give me a number between 6 and 11. 7. Ryan and Davis. 1, 2, 3, 4, 5, 6, 7. Ryan, you're it. You're gonna show your answers for this along with other people. Okay, so let's see, how many markers do we got? All right. Let's see. Lucky number 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Bryce. 1, 2, 3, 4, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Bethany. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Wyatt. Yeah, 1, 2, 3, 4, 5, 6, 7. Caleb. You're it too. All right. So whenever you're ready, you guys come to the board. You can go anywhere around the room. Those of you who have a marker, I want you to come up and show your answers. And Ryan, I'm gonna. Okay, hold on, Ryan. I'll tell you when. I'm gonna show the class your answer. Let me show you guys where, so you guys can see what's going on here.
Damn big. I think it's right.
Actually, Ryan, if you're able to put your camera, can you face your camera down so that it's just showing your paper the whole time? Not that we don't want to look at your lovely face, but we don't. Look at that beard. But if it works, you can. Yeah, there you go. Okay, now turn it around. And okay, hold on. It's just focus it there, right there. I can see it. All right, I think can you hold it there, or if you can put another side? Yeah, we can see it. I can see it like that, I think.
Okay.
All right, did everybody get up? That's up? All right, so let me check. Ryan, I'm going to start with you. Wrong. Damn. Wyatt. Wrong. 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 Okay, so I'm doing so good here. Does anybody have a different answer that's up on the board for an extra credit point that wants to come share what they got? But it needs to be something different than what's up here, of course, because all of these were wrong. But nobody's right. I think somebody's got to be out there. What do you think here? Each player has a penny. Each player chooses head or tail. So I got some headers or tails. So on this part, I'd say Wyatt's and Ryan, I think you had this okay on your. Let me see your. Hold up your paper again. Yeah, so you had that. So the head or the tail. So this is not right. This is good. So you got your choices here, right? So that's a good start. All of these are correct on that aspect. Player 1, player 2, okay? And if player 1 matches, there's a win. So player 1, this has got head or tail. So does this help us having head or tail in here too?
Yeah.
No, because we've already got the head. Head is already identified here. right? So what belongs in the cell? The wins and the, right, the payoff. Remember, it's called the payoff matrix. So we've got some numbers in here, here, and Ryan, what did you have? Did you have numbers in there? No? Okay. So, but these are still wrong, but they're getting close. So think about the game. What's wrong with these payoffs?
Should they be with two?
Should be -1. 1 and -1, right? So in reality, of course, I stole Dirk's penny, but in reality, each person had a penny to start with. And so when I won, Dirk lost his penny, right? And I gained not 2 pennies, but 1 penny, right? Because I already started with 1. So the payoffs are 1 and -1. So go ahead and rewrite that matrix up. I'm going to turn Ryan and Davis back here. Bo, question?
That only works if the actual question says you lose the penny if you win.
Yeah, you didn't state that in your rules.
I mean, if you
Well, what else were you losing if you don't?
Well, if you just win and loss, and you just add it up.
You just said who wins. You didn't say if one gets the other thing.
It's not my fault that you guys can't follow the instructions.
You're
Alright, thanks. I'll grab that after, hopefully. But remind me, throw that second. Hey, who's back there? Can you throw that thing? Let's see how, we got a nice long, can you just slide that down here? Let's see how this works. Yep, slide it down. Come on, come on, oh!
Start over.
Rejected. Alright, there we go. Nice. Okay, so on this game, we've got the agents. So the setup's always the same. You got the agents. You've got the choices of each agent. Whoops, this is a tail with this game. Heads, tails, inside the cell. If they match, who wins? Player 1 wins. So if they match, player 1 wins a penny -1, right? And also wins if they're both tails. So we can do it that way. And then they're flipped. If they don't match, player 2 wins. So it's -1, 1, and -1, 1.
But for us, that wasn't accurate because they were both 5 penny.
Well, that I will give you. That was a bit of an assumption on my part. So, all right. So, where do we end up? Nowhere. Why? What do you mean? Someone loses, someone wins. So, where do we end up with? What's your prediction with the game? Whenever we see this, economists are in the prediction business, right? Economists are in the prediction business. So we want to figure out where are we going to end up? Where are we going to end up with this game using our economic logic? Where's the dominant strategy? Does either player have a dominant strategy? No. No, right? So dominant strategy is if player 1 chooses head, what should player 2 do? Player 2 should choose tails, right? Because 1 is greater than -1. But if player 1 chooses tails, player 2 should choose heads because 1 is greater than -1, right? So no dominant strategy. It turns out there's no dominant strategy for either player. Tip number 2, Nash equilibrium. How many are there up here? 0. So if you work your way around the cell, would player 1 like to switch? No. Player 1, careful, kind of train your eyeballs here. 1 is greater than -1, so player 1 doesn't want to switch. Would player 2 want to switch? Yes, right? And then we come over here. Would player 1 like to switch? You betcha. And so we've got nobody there. Hold on, we're not packing up yet. We got time, right? I got plenty of time left, so no packing up here. So, what is the predicted outcome? What's the best way to play this game?
There is no.
to be clear.
So let me do a little something with Dirk here again. Let's say we're gonna play a infinite game, so no ending point, right? I have a strategy in mind. Okay, Dirk, you ready to play?
Sure.
And who's player one? Just to be fair here. I'll be player one with a match. Okay, I'll be player one with a match. And so 1, 2, 3, go. They don't match. Dirk wins. I have heads. He's got tails. 1, 2, 3, go. They don't match. Dirk wins. Go. They don't match. Dirk wins. I'm not doing so good here. I'm gonna get you this time. 1, 2, 3, go. Ah, they match. I got a head. He had a head. I win. Okay, ready? 1, 2, 3, go. Don't match. Dirk wins. 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 I had heads. He's got tails. 1, 2, 3, go. 1, 2, 3, go. 1, 2, 3, go. 1, 2, 3, go. What was my strategy? To stay the same. Was that a good strategy? I did win with it once. Right? So my strategy was to play heads every time. Was that a good strategy? No, because eventually Dirk picked up pretty quick, actually, that was, if he plays tails all the time, he's going to win a lot of money. What is the optimal way for you to play the game? If it's a repeated game that's played infinitely, switch it up. How often? What probability should you play heads or tails with? Okay, good, because if I played with a die, if I took a die, a single die, and every time I got a 1, I played heads. Every time I got something else, I played tails. Would that be a good strategy for me to play that randomization technique? No, why? The probability, I'm still playing tails most of the time, and if Dirk's perceptive, he's going to say, oh, seems like Russ plays tails a lot of times, I'm going to start playing heads, right? And so the optimal way to play it, you guys said 50-50, the optimal way to play the randomization technique, flip the coin. You got to play a randomization technique with a 50-50 odds. You can use the die, but 1 through 3 play heads, 4 through 6 play tails. All right, we'll pick up there on Wednesday. Thank you.
Couple money back.
Oh, thank you.
Dude, I have to change my bearing.
Any other markers out there?
Yeah. It's all right. It's only it's a 2-wheel drive. It's on the front, so it's all right.
Question?
No, it's all it's
This is organized from highest score class to lowest score class. This is the last 450, 12, 90. And this is like my econ stuff. And there's the midterm. Perfect scores, average scores.
right.
Yeah, so we have to go.
Yeah, that's the only thing I'm worried about. Is there's 3 holes, but if either of those break, I don't know what to do.
Well, why don't you order them now?
Like, they're just standard grade 8. Yeah.
Oh, so you can just go.
Yeah, you go to Washington. Yeah, I mean, it's going it's still $200.
There's always, I've always learned now that we're going to hard now.
So you can make up a lot of points there. That'll make a big difference. You can go back. Those are the ones you can do anytime during the semester.
Talk about basketball.
So yeah,
Yeah.
I'd say look at this guy here, 82. You have 78.
Not that
You go in and hit those extra points. You might even be pushing into the game.
I started
So get on it.
started.
I know.
basketball.
I need to get that.
Did it become easier though? What did you think of my changes?